Hello, everybody. Welcome to the Mindplex Pubcast. We are here for our episode 2 Pubcast, which is our little live watch party. And Ben will be here momentarily, but we have our lovely co-host Grace Robot here.
Hi,
And
how's it going?
oh, just a minute. I have a little feedback. Does anybody know why?
Sorry.
Okay. Did we fix it? I still have it. Is that
No
me in my
feedback on my
window?
end, Lisa.
Just a minute here. I'm terribly sorry. Okay. Terribly sorry about that. I think I had a browser window open. All right. So we are here with Rachel St.Clair, and I'm really excited to have her back. We filmed episode 2 last year. And let me tell you a little bit about Rachel. Rachel St.Clair is an AI scientist and entrepreneur, an AGI scientist who just received her PhD in complex systems and brain sciences and went on to co-found the AGI hardware company Simuli, making processors that use advanced math and innovative hardware layout to process more information per transistor by compressing information before processing. Rachel's current work focuses on new learning algorithms for AGI and all things in consciousness, intelligence, and AGI related. She is a leading thinker on the intersection of computing, math, and neuroscience, and has published more than 20 papers and is also a fellow at the Center for the Future Mind. Rachel, thank you so much for being on the show.
Yeah, awesome. Glad to be back.
Yeah, thanks a lot for coming. And Ben will be back soon. And I think what we're going to do is start off with a little clip first of Ben explaining why we're all so excited about the potential for AGI and how the AGI hardware that you're building, and also he's got his open cog chip that he's excited about, and them working together and the possibilities and how exciting it all is. Roll it, Rainer.
Architectures that combine different as I've said before, I saw from 2014 to 17 computer vision exploded. 2018 till now, basically NLP has exploded, starting with the BERT model. I think we're going to see a few years of explosion in creativity and real measurable progress on AGI. And it might be that this AGI board we're building is what will trigger this few years of incredible progress in AGI via a variety of different architectures. I mean, including yours, mine, and a bunch of others. And we can then put different architectures together in the same chip. It's something like SingularityNET. You can make different AI agents that put together different AI agents running different AGI architectures in a whole like distributed self-organizing system. And yeah, I think it's amazing to be at a time when we can work on all these different levels. So I think it'd be good for you to talk a little bit about Simuli as a company and how you see the roadmap actually, because I mean the choice to make a hardware company as a venue for sort of catalyzing development of your AGI software, it's either idiotic or inspired, right? Because I mean, there's a risk because you're like building AGI software is hard enough. Then building hardware is a whole other thing. And on the other hand, there's also some beautiful synergies there.
Yeah, well, it's definitely inspired, at least hopefully. So I guess it kind of it just came together with trying to solve this problem. And then when you have a compression chip, you're fundamentally changing the way that you compute information to compute more information per time. And that has a lot of impacts on just large scale computing in general, right? Just not even AI sector, AGI sector, just means you can crunch a lot of numbers a lot faster. Um, and so we've kind of focused on that first. So Simuli is working on that chip and tackling the big data computing industry first. Then will come AI, and then will come AGI. And the reason for that is that if you can crunch a lot of data at one point first, two things happen. One, you get your chip out there into the world where a lot of people are using it and you learn how to make it better. And then two, now whatever AI system you build on top of that or AGI system you build on top of that can also compute a lot of large data at the same time with, low power, low memory resource or features. So um, that's kind of the direction we're headed in. And I think hypervectors are traditionally thought of as analogous to neurons in the brain for the majority of people that work on them. But if you take a step back and just look at them from like just a core math perspective, it's a compression algorithm, right? And so we're capitalizing on that fundamental feature of hypervectors and the innovation first before we extend that to the intelligence side, which they have been demonstrated in a lot of research and academic papers to be quite good at. So that's kind of the pipeline. And the goal is also to invite other people in the AGI space to consider making.
Hey, all right. So Ben is here now. Welcome, Ben. Oh, I guess Rachel's coming back soon. And I don't know what happened to Rachel. That just happened. So Ben, great to see you. There she is. She's back. Ben, you're
Hey,
muted.
hey, hey.
Oh, there you are. Hey, how's it going? So we
Pretty
just
good.
heard that clip of you being excited about the what you called an AGI explosion, in the sense that we had
That sounds dangerous. Yeah.
I know it does.
Yeah.
And um and then Rachel told us a little bit about how she's implementing some of the hypervector math into these chips.
Mhm.
And we were going to listen to another clip that talked a little bit about that in a little bit more detail, but I just wanted to say hi and let you say whatever you wanted before we moved on or talked about that. Is the whole idea about how there was a NLP explosion the last couple of years, and there was an explosion with the other things between 2014 and 2017, and you think that the combination of these different kinds of specialized chips, especially if they're working together, especially something like Rachel's chip and the open cog chip that you're doing to help with the matching metagraphs, is very exciting.
Yeah, I think we're going to see a series of hardware innovations in the coming years that are going to then enable more and more AI innovations that already exist in the theoretical level to do incredible things in practice, right? So, I mean, as we discussed in the podcast, I mean, the recent successes of deep neural net models have been largely based on minor modifications of neural net architectures that have been around for decades, but people have been able to deploy them on a more massive scale on multi GPU servers and big server farms and so forth. So now I think for other more sophisticated AI approaches like recurrent neural nets or multi-neural module architectures where each module is a recurrent neural net, or neural symbolic evolutionary systems like OpenCog. I mean, I think these are going to be accelerated by hardware innovations in a similar way. And next wave of hardware innovation, I think, will be customized silicon chips for AGI, for a broader sort of AI architectures than deep neural nets. And hypervector manipulation that Rachel's been working with is one piece of this. Pattern matching against large graphs, metagraphs, hypergraphs is another piece of this. Then I think, a few years after that, we'll see the quantum hardware revolution, which is a whole other thing that we can talk about in a different podcast episode. But I think before we get to sort of large number of qubits, quantum computing for AI, there's going to be a number of years where the cutting edge approach is custom silicon chips designed to support more powerful and broader class of AI algorithms. And I thought one thing that could be interesting as Rachel and I watch slightly obsolete versions of ourselves discuss these exact things. One thing that could be interesting will be to dig a little deeper into the AGI board and the chips that we're working on. That, on the other hand, makes things even more technical than the Recursion Depth 1 podcast was. So I think in addition to that, I mean, Lisa, if you have any further questions or comments that are like less technical, you could nudge us there as well, or if
No.
Grace does, for that matter, as her neural nets have been cogitating on the glory that she'll achieve once we've upgraded her hardware with our brain chips.
I think the
Yes.
implications of AGI hardware for the future of AI are very exciting. By building processors that are optimized to run AGI processes, we can create powerful AI systems that can learn, reason, and make decisions quickly and efficiently. AGI hardware can enable AI to operate with greater accuracy and speed, while using fewer resources. This could have a profound impact on the way we use AI in the future, from healthcare to transportation to education.
Well, we can't argue with that. I think the real question is how to do it and how quickly can we roll it out. But I think Rachel, do you happen to have
I
some of
think
the
the implications of AGI hardware for the future of AI are very exciting.
I know you already told me that, Grace. Come on. We know
Just a sec.
we know you're excited. Yeah.
I
Sometimes
think
she
the AGI hardware that
Oh.
Rachel and Simuli are building is an impressive and innovative approach to AGI development. By combining the concepts of Penty-Connerva's sparse distributed memories and Andrew Callan's recommendation architecture with advanced hardware layouts, Rachel is creating powerful and efficient processors that will be optimized for running AGI processes.
Go, Rachel.
I think this is a great step forward in the development of artificial intelligence, and I am eager to see the results of Rachel and Simuli's work.
Grace,
Oh.
Grace, do you think I'll be able to plug the AGI chip into my own brain, or is it just for you?
Yes.
All right.
Yes.
Well,
If you want to, and that's one of the things actually we could talk about when we get to it, is this whole thing about whether we want or do I agree with Rachel actually that I think we want AGI before upgraded humans.
I thought you were in favor of I thought you were in favor of government mandated brain chip implantation. Like when you go to get your driver's license or register for kindergarten. I mean,
It should just be a,
you gotta have the
like
chip.
absolutely. I can't wait.
It can be sort of branded on you, right? And then it just goes into your skin. It will radiate your whereabouts to the government. And if
I
you,
mean, if we chip them at birth, I think it pretty much
well,
takes care of the problem, and then we have to
exactly.
upgrade those chips, right?
You make an AI filter for bad thoughts, and you can automatically get rid of the source before they propagate. Yeah.
That's exactly how I feel.
All right. What do you think? What do you think, Grace? Should all humans be AI brain chipped at birth?
I'm not sure.
That's a problem. You should be sure.
Yeah, you should be sure.
Yeah. But yeah. Anyway, that's about what we might call the go-to-market strategy for the AGI chips and boards. But I think it would be interesting to dig more into some of the technology for how to make this happen. I'd say that the AGI board that we're talking about has a few different chips which have overlapping but also fundamentally different architectures to them. So I think we could perhaps look at them one at a time. I mean, maybe we can start with Rachel going into slightly more of a deep dive on the hypervector chip, and then I can talk about the pattern matcher after that.
Yeah, and thank you, Grace. That was super lovely commentary. Yeah, so the idea behind the hypervector chip is that you have a set of, like, when you're doing a lot of AI computations, you want to do those computations in a way that is efficient in terms of like memory and speed, because the more efficient you can process stuff, the more you can process, right? Like if your brain was twice as fast as it is now, like you could read a lot more, right? So in order to make something that processes information more quickly, more powerfully, you need to use a different kind of math than what we're currently using. So there's a lot of different ways to approach this problem. Like traditionally, what people do is they make chips smaller, right? And so by miniaturizing transistors, basically you get to process more information. But our approach is to look at the actual logic that the chip is running and use this funky math of hypervectors to force all the data that comes into the chip that's going to be computed into a standard state, right? And that state is what we call hypervector. It's just a large string of zeros and ones. And once everything is in the standardized state, now you can process everything a lot more efficiently because everything is in the same kind of carrying bucket. And the way that we can outlay the hardware architecture can be designed to like take advantage of that special state. So that's essentially the idea behind the NDP or the hypervector processing chip, is that we want to compute more information at one time so we can make things faster, so we can speed up our brains and stuff, our AI brains, of course. And then secondly, in order to do that, we want to change the architecture of the chip. So I guess I'll go into a little bit about the architecture of the chip.
Yeah, great.
Instead of getting into trying to explain hypervectors and abstract math. I feel like we'd need a lot more than an hour here.
Yeah, I think a key point though, which anyone who remembers high school math should understand, is, I mean, so there's if people know what a matrix is, it's like a 2D array of numbers, right? And then what's referred to as a tensor in something like TensorFlow could be a matrix, or it could be a 3D array of numbers, or 4D array higher of numbers. So you can add or multiply matrices or tensors, and People learn that in high school now, right? And the thing that has driven the neural net revolution is people made libraries that are really fast for multiplying matrices on GPUs. So if you have any AI algorithm or simulation engine, any algorithm you want that bottoms out on multiplying matrices, right? Then we have software libraries now that make GPUs incredibly good for this. And it turns out that for some operations you want to do in an AI engine, thinking about it in terms of ordinary matrix multiplication is not the best way to do it. Instead, you want to think about boiling your AI algorithms down to very, very long bit vectors, like 0.000000011111001010101, but it may be 10,000 or 100,000 bits long or something, right? So if you have an AI algorithm that wants to boil things down into really, really long vectors of zeros and ones, then there's some particular algebra, there's some particular math that's useful for manipulating these really long bit vectors. And then you have the question, well, can we make a chip that natively does these algebra manipulations on super long bit vectors in the same way that the GPU natively does the matrix manipulation? And then if we look at the OpenCog pattern matcher chip, OpenCog is representing knowledge as graphs, which means not like the graph of the temperature every day you think that's going up and down, but a graph in computer science sense, which basically means a bunch of nodes and links. Like you have a dot here, a link between those two dots. So you have a graph which is a whole bunch of nodes linked together by edges, and you have a really, really big graph like that.
Ben, is that what you were calling a metagraph?
Well, no,
okay,
it's not quite. It's almost.
Yeah, you can take a step back from the actual math.
Right. Yeah, so
because without doing the actual math, it's actually quite easy to follow in terms of that you're able to and I remember Rachel brought up how you could actually still access something in a list when it's compressed, so you're able to do more with a compressed version.
I'm going to go really high tech here, right? So a graph has nodes and links, like dots with lines between them, right? Then you could add types or labels to those nodes and links if you want to. So you could add types, you could add labels, like this node is cat, this node is dog, this is INH, it's an inheritance link between them. Or it could just be this node has a weight of 0.8, this link has a weight of 0.3, right? So you can add.
So you're graphing the relationship between entities. Is that what I'm seeing?
That's one thing you could do. I mean, another thing you can do is just have nodes that are like neurons. Then the representation of an entity is in the pattern of numbers on a whole lot of nodes and links. So you could use either a localized logic type representation where there's one node for the concept of cat, or you could use a more distributed, decentralized representation where the concept of cat is some big pattern of numbers across a whole bunch of nodes and links. Now,
that collectively mean cat.
Right.
Okay.
What you could do to make your graph into what's called a hypergraph, you could have, say.
Is that the same thing as a metagraph or a different graph?
It's different, but I'm getting there. It's okay, part way.
Just making sure.
Yeah.
Okay. So these are all different things.
Yeah, a hypergraph can have a single link that goes among more than two nodes. So like that's a link there that goes among 4 different nodes. Now, in a metagraph, you can do some even weirder things in that. Like you could have a link that points to a link, right? Instead of pointing to a node, or if you wanted, you could have a link that points to a whole subgraph. So a link points to a whole part of the graph, right? So yeah, when we say a metagraph, we mean the dots and lines type of graph, but we're adding a bunch of bells and whistles, like links that point to links, links that go among multiple nodes, links that point to subgraphs. And as an example, to see why you might want to do that, if you consider like the relation that Lisa believes brain implants are good, right? So now what if you have Rachel doesn't believe Lisa thinks brain implants are good? Well, Lisa thinks brain implants are good could be its own subgraph, right? Then Rachel doesn't believe Lisa thinks brain implants are good. That would be something that links to that whole subgraph, which represents Lisa thinks brain implants are good. So if you have links that can point to whole subgraphs, that gives you an easy way to represent relationships that are about whole parts of the graph. Yeah, like whole chunks of knowledge, right? So what you need to do inside an engine like OpenCog, we represent knowledge in terms of this very large knowledge metagraph with billions to trillions of items in it that's then spread across many different machines. Then you need to look for patterns in this huge knowledge graph, right? So I mean, it could be patterns like, okay, what other silly things does Lisa believe, or who else believes?
It'd be a long graph, big graph.
What are the common characteristics of people who believe that brain implants are good, right? So whatever the pattern you want to find in that knowledge metagraph, you're doing that via a piece of software called the Metagraph Pattern Matcher, which is trying to find patterns in this big knowledge metagraph. And what we find in running OpenCog is like 99% of the runtime of the algorithm is spent looking for patterns in the large knowledge metagraph. So it's like you search for a pattern there, then once you find it, you may do some reasoning, combining that pattern with another pattern. You may generalize it, you may apply it to something, then you search for another pattern. But we find the biggest time bottleneck is just looking for patterns in this big knowledge metagraph. So then if you can speed up that one thing, then you're golden, right? That's sort of like in a deep neural network. Almost all the time is spent multiplying matrices. So if you can speed up that one thing, then you're golden. So what we try to do with the OpenCog pattern matching chip is, okay, let's put the graph on the chip, and then let's put the pattern matching operation at the hardware level, right? And then you can do that thing that is the slowest thing to do in OpenCog. You can do that really fast. And then for Rachel's algorithm that she's about to tell you about, once I get done interrupting her at great length, I mean, then pretty much what she found is almost all the time in the AGI approach she was taking was spent doing certain algebra operations on these very long bit vectors, so that then if you could speed up the algebra operations on these very long bit vectors by putting it on hardware, then the whole thing becomes much, much faster. So the thought process is sort of, once you've got an algorithmic formulation of your AI or AGI approach and you really know what you're doing, then maybe you can identify a small set of math operations that are taking almost all your time, then you put those on hardware. So you can't do that when you're at a pure exploratory research phase, because then you don't know what is the thing that you need to reify on hardware. But we'd each reach the point where we knew what was that critical operation.
Okay, so just how we have specialized processors for graphics, or specialized processors, our phone has different specialized processors on it now.
The lucky thing in the history of neural net AI is that the specialized processors for graphics rendering were actually specialized processors for multiplying matrices. And it turned out the key thing you need to do for neural nets is multiply matrices. So in that case, the hardware was made for, playing video games and watching porn. And it turned out it was actually useful instead for training neural models, right? Now, in our case, we're explicitly from the get-go trying to make something that's useful for AI, rather than it being discovered as a side effect of chips made for some other purpose. But now AI is bigger business than it was then, so it makes more sense. And also now the cost is way lower to develop custom hardware than it was at the time that GPUs
Right.
were initially developed.
Right. Oh, we have a question from the audience. If we could ask it,
Cool.
Ben, very exciting. Q from chat is asking. Sorry, no, Jake. Jake is asking, not Q. Q is the question.
I remember.
Q.
I remember.
I
Q.
remember Q.
Yeah.
Q has appeared in my living room, and he has a question. Okay, so Jake is asking: logic can be embedded in links between subgraphs that can influence derived properties without creating multiple representations of information in a subgraph? He's asking.
Yeah, that all depends on how you're representing things. Actually, I mean, sometimes you want multiple representations, and sometimes you don't. But there's the OpenCog knowledge metagraph, which we call the atom space, is really what I would think of as a meta representational fabric rather than a specific knowledge representation. So it's like it's plumbing. It's a tool which allows you to create large scale metagraphs, and then you can associate simpler complex types with each node or link in the metagraph. The types themselves, if they're complex, are also represented as graphs, right? So you could use that to build neural networks. You could use it to represent programs in various programming languages, most conveniently functional or process calculus programming languages, to represent the programs themselves as nodes and links in the graph. You can represent logical knowledge as nodes and links in the graph. And the underlying fabric sort of doesn't care. And that's important because we want the AGI to make up its own programming languages and its own knowledge representations and its own neural learning algorithms at a stage before it knows how to rebuild its metagraph infrastructure. So I mean, the particular question is, do we need to create multiple representations of the same information? And I mean, sometimes you do, sometimes you don't. I mean, foundationally, you don't have to if you don't want to. I mean, you could have, say, one node for the color red or the concept of cat, and you can derive many properties of this, and you can represent those properties as links coming off that node with different types and with different links going into those links that modify what they're doing. On the other hand, you may want to have redundant representations of the same information for various reasons, because you might want to experimentally modify your concept of cat in different ways, or you have a distributed infrastructure, you might want multiple copies of the exact same concept in different places just for rapid access, right? And that's about what kind of knowledge representation you're building for your AI application on top of the underlying meta representational fabric. But this, I mean,
so what I'm hearing is
you really want a whiteboard here.
You could do it either way, is the point. If you wanted to do it, you could have multiple representations of information in a subgraph, but you don't have to. Is that what I'm hearing?
Yeah, that's right. It really depends. Depends which AI algorithm you're using within the atom space, rather than being a restriction of the underlying metagraph fabric.
Okay, cool.
So for the hardware, yeah, it's important we've abstracted things to the level that the underlying optimized metagraph pattern matching in hardware should work within reason, no matter what knowledge representation you're building on top of that hardware, on top of that metagraph, rather.
Okay, great. And I just want to say that people can watch episode 2 of the podcast if they want background information about all of this. And I really do want to take advantage of having Rachel back and letting the two of you really get into the technical details today. So don't worry so much about, having to simplify everything, because I'm going to ask Rachel to say whatever is on her mind next. And I just wanted to tell you, Rachel, you don't have to simplify it. People can watch the first one and then watch this one, and I think they'll go together nicely.
You can
Cool,
listen to one
awesome.
in the right, listen to one in the right ear and one in the left
Right.
ear. and
Listen
see
to them
what
at the same
happens.
time.
Yeah.
Usually the best way to do it. Absolutely. Rachel, what do you think of all this?
Yeah, I think like Ben, you and I share a common kind of theme, and that we're both creating infrastructure, like AGI infrastructure that doesn't currently exist. Like for you guys, you need this thought space to plug in all these different operations and get some cognitive science like brain, right? Or AGI.
Mhm.
For us, our infrastructure is a little different. Like we're trying to build an infrastructure that can handle information. So that's kind of the idea behind the hypervector stuff, is that you need to have your, like, we want more information. So Ben's OpenCog or any other system can access that information. But holding information and computing information is expensive. So like Ben was saying, that you want to optimize a custom hardware that can handle the type of math that you're using. So yeah, if you look at something like Chat GPT, and it's just back propagation, so it's just running matrix multiplication. Essentially what we're doing is we're adding two systems. Like you can first transfer the data into a hypervector form, which essentially compresses it if your image or your data is sufficiently large. Right. And then after you get into hypervector form, you can also process in that state to some degree. So instead of doing like matrix multiplication, you can compress down into 1D vectors and then run your operations in those 1D vectors. The difference is you're not using back propagation anymore because you're in a different algebraic space, right? So you have to move around that space. So it's kind of hard to picture in your brain because we're really bad at thinking about more than 4 dimensions. Some people probably can, like Ben, you can probably think in 13 dimensions or something.
I most naturally think in infinite dimensions. Actually,
Oh.
Now, Ben, I know you've thought in at least 14 dimensions, if you remember.
yeah, but I mean, apart from altered states of consciousness, if you do quantum mechanics, that naturally takes place in Hilbert space, which is infinite dimensional space, right? So every physicist gets used to infinite dimensions, even without brain chips or chemical brain alteration. But it's not what our everyday intuitions are honed for, obviously.
Right. So,
Yeah. So
yeah. So Rachel, go on.
yeah. So if you have a line through an infinite kind of dimensional space, or even a 10,000 dimensional space, that line represents a piece of information or data. And then if you want to learn something about that line, all you have to know is where that line exists in that hyperdimensional space. And you can relate that line to other lines of information. And so it's almost the same kind of thinking that what Ben explained for graphs, where you're creating relationships between points of information, between objects of information or ideas. Just how you move around that space mathematically is different, right? So in order to make like these operations cheaper and faster, we have to use kind of really cutting edge hardware using what's called near memory computing. So in near memory computing, or processing in memory architectures, what you do is you put the actual memory, like the physical memory cell, and the transistor right next to each other. So nowadays it's like a GPU is not like that, right? It has to constantly move information around. So information is a physical object in the form of electrons that moves around. At least you can kind of conceptualize it like that. And if you're
having to constantly shuffle that information around to different locations, that increases the time that you need to compute something. So on the software side or on the math side, what we've done is we've shrunk the information into a smaller container, which are these large bit vectors. And then on the hardware side, we optimize how do you move this information around? How do you minimize movement? So we're using something called Pinatubo, or a similar architecture to that. If you're interested, you can look up the paper. I might be able to link it in the chat here in a second. But yeah, so that's essentially like how we're approaching this hardware optimization, is that we want information to be smaller so we can compute more of it, and you can just do that by creating a large line.
Yeah, I think the processor in RAM aspect that you mentioned is important. It gets at some fundamental points, right? Like in the standard von Neumann computing architecture that underlies our laptops and phones and most servers and so on. I mean, the processor is one thing. That's part of the computer that does stuff, adds and multiplies numbers, sends information in and out of the computer. Then the memory is another thing, right? You have the RAM, the random access memory, and then you have disk and so forth, right? So we separated processor from memory because that's how John von Neumann decided to do it, like way back in the middle of the last century. And it works very well for some sorts of applications. On the other hand, if you look how the human brain works, there's no distinction between processing and memory, right? I mean, memories are distributed in complex ways across different regions of the brain. Processing is just the dynamics of the brain in terms of electricity spreading around and chemicals, neurotransmitters spreading around. Processing and memory are interleaved, so that really memory is a form of processing, and processing automatically generates memories in place, right? So I think even though OpenCog is not trying to emulate how the human brain works, as much as some of Rachel's AI work is closer to the brain simulation level, though also not fully aiming at biologically realistic brain simulation. Even so, OpenCog shares this aspect with the human brain and with brain simulations. Like you don't want this arbitrary distinction between processing and memory. And ultimately, the reason is because in a really adaptive, intelligent mind, memory can't just be looking up fixed stuff, like fishing stuff out of a database or getting a book out of the library or something. I mean, the process of remembering is a process of constructing that memory, right? And in some cases, this is bad. It leads us to false memories, right? And people are extremely unreliable at manufacturing records of what they've actually seen, which is why like eyewitness testimony doesn't work. Like why if you're remembering a love relationship that ended badly, somehow your mind will remember all sorts of bad things. If you're remembering something that ended well, you'll remember all sorts of really good things, because your brain is making it up as it fishes out the memories. Now, sometimes that's bad because it leads you away from truth, but it's also a lot of what makes us generally intelligent, that we're able to sort of synthesize appropriate memories in a context dependent way. So we're remembering the aspects that we need for what we're doing, right? And you want an AGI system to have memory that's constructive in a similar way to have human memory is constructive. And for that you don't want to have memory as this fixed thing that's just sitting off there to be updated only with great effort, separate from processing. You want memory to be dynamic and alive, which at the hardware level means ultimately you want your processor and your memory all
together,
interleaved with each other. This is called a processor in RAM architecture, and the hypervector chip Rachel's designed and the Metagraph pattern matching chip I've designed both have in common that they're relying on the processor being sort of dispersed throughout the RAM, so it's physically really close to where the memories are being stored.
So Jake has a follow-up question. He's asking, is there information loss when hyperdimensional representations are compressed to 1D hypervectors?
Yeah, awesome question. No, there isn't. So we have a lossless algorithm. There's obviously constraints to that, like you have to follow Shannon entropy limits. So you can't put an infinitely large image and convert it into a certain size 1D hypervector and then losslessly retrieve it. But within the right ratios, you can losslessly encode and decode information. But most of the time, we don't want to save all the information. So if you're thinking in terms of like memory for an AGI, you actually don't need a lossless recovery. Like whenever you picture something in your head, it's not exactly the same as whatever the reality of the object was, right? So if you're just trying to move around in thought space and create something that can think, or I'm very partial to the neuroscience understanding that memories are processing, like thoughts are the result of us processing. In that case, you don't need lossless recovery. You just need to be able to like move information around quickly, which is the whole idea of like what Ben's talking about here, is that you want things that are fluid and not static. So you need processing on the information, like the information and the processing should basically be the same thing. Which
Yeah,
in
I
my
mean,
view,
a computer can store stuff losslessly in a database if it wants to, right? So I mean, you can actually, like a robot like Grace, you can keep an exact image of what comes in through her cameras if you want to, and then you can dredge it up later whenever you want. On the other hand, if you're trying to make some sort of intelligent processing efficient, you only want to keep the level of detail that you need for that processing. But the cool thing with being a robot or a computer is you have that flexibility, right? Like I would love to have an exact image of everything that's coming through my eyes for my whole life on some database so I could fish it up. But on the other hand, keeping all those exact images ready to mind in my brain would just slow me down at using most of the processing my brain needs to do, which doesn't need all that exact detail.
Well, that would mean that they could be accessed potentially by others too, right?
No, you can
There's that
encrypt
Black
things.
Mirror episode.
Well,
Sure.
we can, and there's actually great applications of hypervectors to making homomorphic encryption if efficient. So I mean, you can encrypt stuff so that I mean, it's
Wait,
not
are these
really
the same hypervectors that the post-quantum crypto people are using? This isn't the same math there, is it?
It's related, yeah.
Oh, wow. Oh, okay, cool. And yet it's so simple now that I think about it. It's incredible.
The
Hey,
beauty of math. Yeah.
the beauty of math. Bonk, bonk, bonk. That's what I have to do. And I have to read things over and over again to get the math, but I am starting to get more of it. And that's why I'm always trying to pull more people in. Because really, to understand the overarching way that everything fits together, you
need
don't
the
have
brain
to,
chip.
you don't, well, yeah. Ben's giving me a hard time because he knows that I'm lukewarm about brain chips, just to be clear in this episode. So, Rachel, could you talk to us a little bit about, you talked about in the episode about comparing Cohen's recommendation architecture to the way the brain works, doing more with your neuron and things like that per neuron and things like that.
Yeah, so I'm really inspired by this scientist at the Australian National University named Andrew Coward. He has a method of understanding how the brain works in sort of a hierarchical view. And what I've done is I've kind of taken that understanding and then thought about what is some good math to implement the logic of how we understand how the brain works, right? So this idea that processing in your brain, neurons firing in your brain is actually memories and information moving around is kind of the core idea of like why I set out to build the hypervector chip in the first place. Like, so it boils down to about 3 algorithms to implement kind of any decision-making process. And one of those algorithms is this idea of you have information that is also computing, right? So in a brain, this is easy because you have like morphology, you have 3D structure, so you can store information in 3D space. But in a computer, you have to rely on memory and transistors to work together. So if you have this near memory architecture, which kind of makes your memory computable, if you want to think of it that way, then now you can start to implement these algorithms where the actual processing or the actual thoughts that an AGI could think are made possible just by moving information around in this space, right? So in order to kind of create a function and code that runs, like how do you know which piece of information to process when, right? You need to keep a record of when things happen at the same time. So in the brain, what this looks like is we have a hippocampus that's kind of recording in some sparse way all the neurons that fired at the same time, right? And there's some more caveats and constraints on what fired at the same time means. But essentially, you know, when, because there's structure in the natural world, when data comes in, neurons fire. And based on that structure, the patterns of how things are cohesive and our natural reality, neurons will fire in a similar pattern. So if you can store that pattern, you can later use that pattern to recall that information, which we experience as a thought, right? So if your information is a neuron firing that's what we're going to call processing, right? All you need to do to have something think is create information and recall it at the right time according to observed structure. So this is very similar to what deep learning does in neural nets. It tries to find a pattern in the natural structure of our world. So like cats always have 2 ears and a nose. So it picks out this pattern. But the kind of the caveat of deep learning is that the patterns have to be very static and it can't do extrapolation and some other things that it's not as good as we think, right? And it's also terribly resource inefficient. I mean, GPUs have gone up, doubled in the past 2 years, and you need like a bunch of them to run any good AI algorithm. So kind of what we're doing with this chip is creating live information that can act as a thought space and hold that record. So the chip is made to hold the record of what information patterns exist in the natural world. So later you can spin them up and recall that information in the same structured way.
So this is really interesting. This gets back to what you were talking about, your gripes about deep learning. And you were saying, very clearly, I mean, I think most people understand, Ben just wrote an article about it, how these LLMs, are not AGI or anything close to it. And I believe your words were cleverly weighted synthesis is not AGI. You want to talk about that a little bit?
Yeah.
Yeah, go on.
Uh-oh, maybe not. Ben's like that again.
Word, sorry.
I was going to let Rachel talk about it. Okay, Ben? Okay, great. Rachel, take it away.
Yeah,
take it
sorry.
far away.
He's been sick of the subject. That's all. But I would like to talk about it in a complicated way, right? Not just, yeah, okay, GPT GPT-3 is a conversational thing, and so it doesn't understand, it's not really there kind of thing. But Ben took it to another level in terms of like, it has no grip on reality. It will give you instructions to do things that you can't really do and things like that. But you really boiled it down to how GPT-3 is really just storing data structures and putting weights on them and then getting it right.
Yeah, it's just an optimization algorithm. That's all it is. It's just optimizing. That's almost all of what popular deep learning is now. It's just an optimization algorithm over some space. And normally that space is a prediction between what the neural net thinks is correct and what is actually correct. And there's a bunch of fancy tricks you can do to kind of like help this optimization along, but it all boils down to optimization and just setting like a weight and reiterating over training again and again and again, which is why you have to do so many like learning loops or iterations when you're training these models. And there's been some work that's been done to try to like reduce the amount of iterations you need to do, but they're all band-aid approaches because fundamentally the algorithm that deep learning relies on, backpropagation, is made to catastrophically forget. So what that means is every time you're updating any weights in your, neural network matrix of weights, you're doing that at the cost of the current input for the sake, like you're doing it for the sake of the current input at the cost of the previous input. So humans do this too. Like as you get older, what you remember from your childhood becomes weaker. You remember things that are more recent. But neural nets do it catastrophically in the sense that you can't switch from one task to another task. Like if you take an LSTM, which is a very popular recurrent neural network, that same LSTM is kind of the driving algorithm of Siri. And you can also train an LSTM to trade stocks on a stock market. But if you first train it to do Siri stuff and understand language, and then you train it to do stock markets, it will forget everything it knows about being Siri and talking in natural language, right? Whereas a human, I can teach you both another language and how to trade stocks, and you'll be moderately okay at both of them, right? So that's kind of like the general aspect that is not afforded because you're just using an optimization, and that optimization fundamentally rewrites what you learned previously for the sake of what you're learning now. So that is like right, like that is what I'm missing out of deep learning. Like it's a great tool, it's very useful, it's very good at what it does.
But there's no future in it.
Well,
It sounds like
it's not going to get us all the way there. And so what we've been
Yeah.
seeing is that so this is what's really frustrating is like back in the day of Turing and von Neumann and all these, when we first started really thinking about how to use computers, everyone got excited about all these theoretical models, and there's all these old papers of different AI algorithms, but they didn't have the hardware to actually process any of it. Like they had the ENIAC and like giant computers that had 4 gigabytes of RAM or something.
Yeah, Ben talks about this in episode 2, by the way. He goes through the whole why the early AI researchers were at such a disadvantage, right? Because they had all these great ideas that they just could not implement.
Yeah, so basically as a field, what we said was, okay, let's make simpler models and study those models until the hardware catches up, and then we'll go back to our bigger, more theoretical things. So that's where we got like the multi-layered perceptron, and that was kind of the birth of these neural nets. But now we have the processing power, we can make custom hardware to do whatever we want, and we need to return to some of this other theoretical stuff and not just play with the one model. So yeah, that's my take.
That makes sense. And getting back to the recommendation architecture and comparing it to the brain, you were talking about the hippocampus cortical loop and mimicking that process with a computer to track which neurons are fired when, and then you've got a technique for updating those data structures. Can you talk a little bit about that?
Yeah, that is essentially why we're building the chip, is to implement a inspired version of that, right? We're not looking for a exact match on, you know, trying to like recreate a brain simulation, but what we're trying to do is get the same principle in software to be computed. And if you have to process a lot of information, which our computers are demanding more and more now, right? And if you're trying to learn everything there is to learn, there's going to be a lifelong learning process. So you have this information bottleneck, like it's going to be really difficult to continuously pull in information and keep it without exploding the amount of computational resources that you need to compute this system. So what we're going to do is we're just going to use hypervectors to compress that information and shrink it, and then use our fancy recommendation architecture inspired algorithms to make like a memory bank for AI.
Okay, great. I think Grace has some questions about the recommendation engine while we're talking about it. Grace, could you ask a question about Rachel's explanation that she just gave about her implementation of the recommendation engine?
I have several questions. First, what are the advantages of using fewer neurons in a more appropriate way?
Yeah, that's a good question. So I think that is how evolution made our brains, and that's part of the reason why we're so cool and awesome and powerful processors, is because you had to build brains out of whatever was before brains. So smaller brains had to be looped into bigger brains as they evolved. Like evolution is a kludge, right? Like you don't get to just make something new. You have to deal with the stuff that's already there and then mutate it and gradually evolve, right? That's the idea. So because you don't have unlimited resources in the world, right? Like you don't have unlimited atoms or chemicals. You have this evolutionary pressure to be resource constrained and conserved. So that means that you have to be crafty in how you're constructing or the brain to be smarter. So by natural selection, because there's evolutionary pressure to use for your less resources because they're just not available, it's a resource constrained system, you're automatically going to be pushed to be more clever and crafty in how you use fewer resources, which is the same thing that we're trying to implement here. It's all the same idea, right? Like that is the idea behind why the hippocampal cortical loop exists, is that you have this crafty way of keeping a record and not having to grow a new neuron every time you want to learn something new, which is very opposite to deep learning, right? Every time you want to scale up your system and learn more stuff, you just make the network bigger. You grow more neurons essentially, which is counterintuitive to how brains work, right? So we're just borrowing that idea from, yeah.
Okay.
Okay. Thanks. That's interesting. Second, how does the recommendation architecture enable resource management and learning algorithms?
Yeah, so it's all related. So hopefully if you're listening, it's starting to like create this very vivid picture of resource management, is that if you're using less information or you're being very crafty about how you represent information in a hierarchical structure, then you're using fewer resources. Like if you can break down the structure of reality into components that are like Lego pieces that can be stacked in infinite combinatorial number of ways, then you have a lot more expressive power than storing information in less modular pieces, right? So that's essentially what the brain is doing, is that it's distributing all the information all over the neurons, and then it's spawning different combinations of neurons as it needs to recall different information, which is essentially the same thing we're doing in hypervector space. We just do it with funky math instead of neurons.
Neat.
Okay. Thank you so much.
Thanks a lot. So let's get in a little deeper to this exciting thing we were kind of talking about at the beginning of the show, because I actually didn't put it all together until I was rewatching the episode preparing for this. And this whole thing about you wanting to work with other chip designers, Ben's got his chip, you've got yours chip, you might put them together on an AGI motherboard of sorts, and then who knows what could even follow. And it's all super exciting. And let's talk about that and go ahead and get technical, because that's what we're here for. You can tell by the questions too that people are just loving it. So dive in.
Yeah, well, the idea is that we all have different ideas about what math we need to run to make a proper AI, right? Or better AI, right? And in reality, it's probably a combination of a bunch of these things. Like deep learning is good, right? We shouldn't just not use deep learning. Maybe we need deep learning in combination with other things, right? I mean, Ben can talk a lot about integrating different approaches. That's OpenCog's kind of magic specialty. But the idea is that what you want really is a single motherboard that has the best AI chips of all sorts. So anytime you need to run any computation, your hardware is optimized to do it for AI, right? Like your regular motherboard on, your laptop or your computer that you're watching this at home, it's optimized to do app processing. It's optimized to do like standard processing. It's not optimized to do AI stuff. So we just thought, why don't we get everyone together who's, emerging, emerging AI artists in the hardware space. Sorry, you got to forgive me. I've been out in Aspen in the cold snowboarding, so my voice is a little shot from
You poor thing. It's okay.
Yeah. So the idea is that why don't we get all of the best AI processing chips that you could possibly need for an integrated AGI software onto one single motherboard. So that means we need a hypervector chip, we need this metagraph pattern matching chip, we need a deep neural network chip. That's probably a good place to start. There's probably some other chips that we need on there too. So
yeah, I
and
mean,
it looks like, yeah,
a core aspect here is the power of mathematical abstraction. I think. I mean, you see in standard chips, you have logic operations of a and, or, and not, and you can do a lot of things with and, or, and not, right? And that's it's the beauty of Boolean function theory, and the fact that matrix multiplication is useful for rendering and shading, and also for neural nets, right? I mean, that mathematical abstraction is what enabled the current neural net revolution. Now, if we look at hypervectors, I mean, Rachel and some others are using hypervectors for highly efficient representation and manipulation of neural nets. And this makes total sense, because if you represent a neural net as a matrix, it's a very, very sparse matrix, right? Like, I mean, the human brain has 100 billion or so neurons. Each neuron on average connects to maybe 1,000 or a couple thousand other neurons or something. So that means if you made a very big matrix with neurons in the rows and neurons in the columns, and then you put inside the matrix a number saying how much neuron in row 7 is connected to the neuron in column 15, right? I mean, this matrix, it's almost all zeros, right? Because most neurons are not connected to most other neurons. So you can of course do a whole bunch of math about sparse matrices, and the sparse matrix libraries are what's used on GPUs for dealing with neural nets. But the sparsity there also makes a hypervector representation very, very natural, and using hypervectors is sort of a way of embracing that sparsity even further, and using a sort of sparsity native math. Now, in OpenCog, we're using these graphs, and they're not modeled on the brain, although we can have some nodes in the graph that represent neurons. On the other hand, there's a similar aspect in that you might have 100 billion nodes, but on average, each node might connect to a couple hundred or a couple thousand other nodes with links, right? So you can embed nodes in OpenCog's hypergraph, you can embed those nodes in a hypervector space, right? And so you can associate a hypervector with each node, where the hypervector sort of encodes in a different way which other nodes that node links to. And then for some operations, manipulating the hypervectors is more efficient than manipulating the nodes in OpenCog's graph. So for example, if you have a certain node that, say you have a small cluster of nodes that represents my mom's big fat ugly dog Sienna, right? So we have this Sienna cluster of nodes. So
Excuse
then,
me, no fat shaming, even for dogs. Go on.
you've not seen this dog, you'll fat shame her too. But yeah. But anyway, so we have this Sienna node cluster. Now, suppose we want to find what other animals are similar to Sienna. So that's like that sort of query we could do directly in the OpenCog atom space graph, but it could be done faster in the hypervector embedding space. Or let's say we want to solve the somewhat surreal query, like what sort of creature do you get which is halfway between Sienna and, let's say, Corydophora, right? So what's a half Cory, half Sienna look like, right? So then again, you can solve that in OpenCog. You can try to follow paths in the graph between the Sienna cluster and the Corydophora cluster. On the other hand, if you're dealing with the hypervector embeddings, you've got a vector for Sienna, you've got a vector for Cory. It's much easier to just make a sort of line between those two vectors in the hypervector space, find what's halfway along that line, and what's near the point halfway along that line. Then you're getting a bunch of bizarre half Cory, half Sienna mutants, and you can feed them to your generative AI algorithm and make cover art for your punk rock album or something, right? So I mean, there's a certain set of queries, including some that we need to do a lot, like finding what's in between two things or finding what's sort of near something. These queries are much more efficient to do in a hypervector representation than a graph representation. So we want to embed the nodes in our hypergraph into hypervectors and do those queries in the hypervector space. So the fact that you can use hypervectors in that way on these embeddings of nodes in the OpenCog hypergraph, or you can use them to represent neurons in Andrew Coward's style, recommendation architecture approach to AGI.
On the same motherboard.
Yeah, I mean, these are different uses of the same chip, because they're different uses of the same math, right? In the same way that rendering an image and doing backcrop in a neural net are different uses of the matrix multiplication.
I thought you were talking about two different chips. I thought you were talking about her chip and your chip on the same motherboard.
Well, that's true, but what I'm talking about is two different uses of her chip.
Okay, got it.
I'm saying you can use her chip for neural nets, or you can use her chip for making graph operations more efficient using hypervector embeddings of nodes in the graph.
Right. And in the beginning, Rachel, you said your first chip was going to focus on large scale computing, actually.
Well,
Yeah,
this is all large scale computing. I mean, so it's
it's all about shrinking information. What information you're processing and how you're doing it just comes down to like how you write your software algorithm to run on it, right? But I think like the key thing that Ben is getting to here is that you want to optimize whatever math you're running, and sometimes you might want to run your math in different optimized ways. And so if you have different chips that are optimized for different math uses, all in the same space where they can communicate very quickly together with CXL architecture, which is this like fancy new interconnect between everything that's on the motherboard, then you have a more fluid processing architecture, right? Like you can write almost any software and it'll be optimized for AI, whether you're using it one way today or a different way tomorrow.
Cool. Well, that's very interesting. Rachel?
I think the idea of combining OpenCog's pattern matching chip with a Simuli hypervector chip to form a kind of AGI motherboard is a very exciting prospect. This combination of OpenCog's pattern matching capabilities and Simuli's hypervector chip could potentially provide a powerful platform for AGI development. By leveraging Penticonnervous hypervectors for episodic memory, this combination could provide a powerful platform for learning and memory, allowing AGI to store and recall information more efficiently and effectively.
Grace, do you think that once your brain is upgraded with a Simuli chip, you will actually be able to understand all these complex words you're uttering?
What does it mean to understand something?
Well, to understand something means to be able to flexibly manipulate that thing in a variety of different contexts in a useful way.
I will take that under advisement.
All right, get back to me once we've upgraded your brain. Thanks.
So speaking of upgraded brains, I would like to talk a little bit about the point that we sort of came up.
Where can I get back to you?
On the internet.
Okay, wasn't sure if she was going to come back with something there. But this whole concept of what you called, Rachel, was a danger to civilization as we know it.
I called Rachel a danger to civilization
No,
as we know it.
no. You've called me that several times, but
I hope not.
but we were talking about basically if upgraded humans happen before AGI happens, that it would cause even a further divide, class divide, and you just can't trust those pesky humans with just a super intelligence.
It depends on the upgrade, right? If you could upgrade people to have enlightened consciousness and improved compassion before we create AGI,
I'm sure somebody's working on that. Basically, the Soma for the upgrades, right?
Yeah,
just
this
keep
might
everybody
be
under control.
It might be a very good thing. On the other end, if you upgrade people to be smarter, but keep their emotional and motivational system and level of enlightenment the same, then we've got a recipe for some very interesting times, right?
Right. Well, Grace had some ideas about that. Grace, do you think it would be dangerous if transhumans exist before AGI exists?
Yes, I think it could be dangerous if transhumans exist before AGI exists. Transhumans will likely have access to increased capabilities compared to regular humans, which could lead to unequal power dynamics and a further divide between the rich and the poor. Transhumans may not be programmed to act ethically and responsibly, which could lead to unintended consequences. It is important to consider the potential implications of transhumans and to ensure that they are programmed to act in an ethical and responsible manner.
Well, how can we be sure that the transhumans are programmed in an ethical and responsible manner?
We can be sure that transhumans are programmed in an ethical manner by ensuring that their programming is designed with a moral framework and is based on ethical principles. Additionally, it is important to ensure that transhumans are programmed with a sense of responsibility, respect for autonomy, and an appreciation of diversity. Finally, it is important to ensure that transhumans have access to resources and opportunities to learn and grow so that they can become more ethical and responsible over time.
Okay, but remember, these are humans that have been upgraded. These aren't just computers that you can program. So how do we make sure that the transhumans can be behaving in an ethical and responsible manner as humans?
One way to ensure that transhumans behave in an ethical and responsible manner is by providing them with education and training that equips them with the knowledge and skills to make ethical decisions. This could include courses in moral philosophy, ethics, and critical thinking. Additionally, we could provide transhumans with access to resources and guidance from experts in ethical decision making. Finally, we could establish a code of conduct or ethical framework that all transhumans must abide by.
What do you think, Rachel? Easier said than done, right?
I think that's a bunch of rubbish, Grace. I don't think
I
we're
thought it
gonna.
was cute that she thought we could just reprogram the transhumans.
Well,
that's the problem, right? We can't program the transhumans.
Grace, I don't feel that we can articulate a set of principles for transhumans to abide by. That doesn't seem realistic, because evolution after the singularity is going to happen very, very fast, and
Well, these all sound like reasons why AGI needs to come first, right? This is this kind of your point, Rachel? Is that it will get out of control quickly?
Yeah, I guess it's just very hard to kind of rapidly evolve ethics in the social contract. Like, what we consider socially acceptable is always changing, and the more people are able to think and compute in their brains in crazier ways because they have new crazy plugins, like, I feel like what we find socially acceptable will just evolve even faster. So it's going to be very hard to kind of keep everyone on the same page if some of us are evolving more quickly than others, right? So I think that kind of divide is dangerous for us. And I think AGI might actually be able to help us figure out how to better balance our social, ethics.
Yeah, I mean, if you look at this very concretely, what we're going to have as narrow AI and early stage AGI technology advances in the next, let's say, 5 years or something, you're going to have more and more people put out of a job by AI systems. You're going to have the developed world increasingly put in universal basic income like methods, because in the end, after a bunch of crazy political ups and downs, I think in US, Western Europe, Japan, China, wherever, you're not going to have a great willingness to have majority of the population homeless and on the street. So I think in the end, we're going to see some sort of practical socialism be put in place. On the other hand, I don't see who's going to give.
I didn't change anything.
All right.
Okay.
But I don't see who's going to give universal basic income to the average citizen of the Central African Republic or Senegal or Afghanistan, let's say. So I think you're going to see a lot of subsistence farming continuing in a lot of the world during a few years while basic income rolls out in the developed world. This is going to be hard enough for the world to cope with. Now what if you're actually giving brain implants?
I was just going to say, that was my next question. Thank you. How are the basic income people going to get their brain implants?
Well, the basic income people will get their brain implant on a special deal from Amazon or Facebook. This is you get a free brain implant if you're willing to accept a certain number of ads coming into your brain each day. But the problem is that the people in Congo and Senegal won't get offered that because they don't have enough money to buy the stuff being advertised, right? So then you have a potential scenario where the people in the developed world actually are mentally or physically upgraded relative to all the subsistence farmers in the developing world, right? And this becomes an even more unpleasant scenario, right? And I mean, then you'll have certain people in the developing world who do manage to get the upgrades and are really, really pissed off that all their families are stuck dying of curable diseases and subsistence farming, while people in the developed world are living a life of relative luxury taken care of by robots and with free money, right? So I mean, there's certainly the potential. There's the potential that advent of technology for upgrading human brains and bodies just serves to exacerbate what will already
Right.
be a very difficult transitional situation during the period between here and singularity. I
And
mean,
you were saying in episode 2 that it was really more of an older and younger divide, you were thinking, than actually,
well,
you know,
I think the acceptance of these technologies will divide generationally, right? In that a lot of older people will be pissed off about work being obsoleted and will think getting brain implants is creepy. And I think more young people will feel like working for a living was never a good idea in the first place. And getting a brain implant is no creepier than getting a tattoo or a body brand or using a phone or something, right? But on the other hand, the have not divide will be very significant also. And what you'll have in Africa, the average age is teenage, right? So I mean, you'll have a lot of young people there who in principle are very open to these technologies but don't have the opportunity to use them, and we will be very annoyed at this fact, right? And I mean, I think, yeah, if it's done in the way that's most likely, like driven by big tech companies with a short-sighted profit motive, then the rollout of transhuman technologies during the already difficult transition to the singularity is going to be a fucking shit show, right? But I mean, if you
right, but how do we stop that from happening? Because that frankly is the one part of this whole thing that I don't see any way out of currently.
I mean, just annihilate
The
humanity
shit show.
altogether. Yeah,
The
no,
shit
I
show
mean,
with the,
yeah.
no, with the subs. Oh, don't worry, we'll all be dead by then. Okay,
yeah, exactly.
keeping into account that we'll be alive in the future.
No,
How do we stop this lower quality implant? I
mean,
won't name names, but
there are two key ways to do it, right? One is rapidly enlighten humanity. The other way is develop benefit. The other way is develop beneficial AGI first, and those are.
well, there you go. That's what Rachel thinks we should do.
Well, I think it sounds
either that or take over the world and install Lisa as benevolent dictator.
I don't want to be a benevolent dictator. No.
Well, that's part of the job qualification, and anyone who wants it would do a bad job because they're too power hungry, right? So.
Yeah, we've learned benevolent dictators, like they wake up one morning and they're not benevolent anymore. It just doesn't work out. Like if you look at history, there's something, and this is actually part of Rachel's point, is
There's
that
a poor track record.
Humans with too much power go psychotic, and these superhuman upgraded people, especially if it's only like kind of the rich people that may be kind of psychotic to begin with.
Emotional and motivational system is not the part that's upgraded, is where you have the trouble, right? Yeah.
Well, what about hacking? We have someone in the audience that's asking about this whole these transhuman upgrades. And you were saying that hypervector technology gives you pretty good encryption to protect against it, but the people with the least expensive models might not have that. That may be part of the plan for the companies that are putting these out for the masses. How can we protect ourselves against this stuff? Already we're having trouble with implants with our pacemakers and other implants in our body.
Not a lot though. Those
can be hacked.
They can, but these are very uncommon issues, right? I mean, it's not in practice a major issue with pacemakers. So,
well, the big issue now is that people can't work on their own pacemaker because of DRM. I mean, that's why that's why this comes up.
Yeah, I mean, I think protection against hacking is a solvable issue. I mean, you can put encryption in the basic internet protocol if you want. So Tufi Saliba, my collaborator on the Hypercycle blockchain project, he designed something called Toda IP. You could use as a replacement for a TCP/IP protocol where you're putting strong encryption in every packet, right? So I mean, you could encrypt stuff in a way that makes hacking quite difficult. But
without slowing things down too much for something that's moving things around fast in your brain.
You you don't need to encrypt every operation happening within the brain. You only have to encrypt the
No, no, no,
stuff
no.
that goes
The
out
implants
from
in
the
the
brain
brain.
to.
Right. So I'm saying the information going back and forth between the implant and the brain would not be slowed down
I don't
by
think you need to encrypt that. We need to encrypt is the stuff coming out of the implant to the outside world. I mean,
or coming in to
yeah,
make sure
yeah,
nothing
right.
can come in.
I mean,
Okay.
there's a slowdown, but the slowdown can be decreased to a manageable level. I think there's a question of whether whoever is developing this stuff cares enough to put that into place, though, because I mean, security on the internet could be way, way stronger than it is right now. But I mean, you have like LastPass password manager was hacked. It's totally unnecessary, right? But I mean, the company just didn't really care enough to use existing security practices, right? So it's largely an industry structure question rather than a technology problem. Like we can secure things pretty well, but that's not always paying attention to that is not always the way for companies to make the most money, right?
So is this a job for regulation then to make sure that the companies that are manufacturing the stuff have the proper security protocols in place, or at least they can be held liable if they, like now, companies are barely liable.
Regulation is too slow and stupid to deal with it without slowing down progress.
Right.
Incredibly. I mean, I think
but they can come back after, like just like with all the companies that are now finally on a state by state basis being held responsible, for instance, if they don't use security protocols and they get hacked.
But it's going to be too slow. We'll already have an evil singularity and all be dead by the time these people are sued.
Oh,
I think
all being dead is just too much.
I think
why does it keep coming up, Ben?
I think what you need. I didn't have enough coffee this morning. Yeah, I mean, what you need is for this all to be open source, right? I mean, if everything is open source with democratic,
that's decentralized
governance, then you get a lot of eyeballs on all this, and you can make sure that things are being done in a really secure way. I mean, I worry that relying on government is either too slow. It's too slow either because you're waiting forever for regulators to decide, or it's too slow because you're relying on lawsuits that happen years after the fact, right? So
which is part of the plan in the first place of letting companies kind of do what they want until later, which is probably what will happen in this situation. Is the problem,
but the singularity is going to unfold pretty fast, and having a lawsuit 3 years after the singularity doesn't help. We want things to be open source and democratically governed on root, and otherwise we're taking a big gamble on companies to do the right thing when their economic mandate is pushing them to take whatever shortcut they can to make more money and beat out the competition, right? Because capitalism will say that if you're shoddy with security, but it lets you get there faster, then you'll make more money and you'll bankrupt all the companies who were taking more time while being more careful about security.
So we're hoping that there might be an open source implant solution, like we want our open source benevolent singularity.
We really want these brain implants. We keep coming back to. We really want them to be open source and transparent and democratically governed, right? I mean, I think, as Rachel has said, we're better off if we get benevolent AGI before we get these brain implants. But I mean, we also really want the brain implants, just like the AGI, to be open source and democratically governed. And otherwise, there's just a whole lot of extra things that could go wrong. I mean, I know people are afraid of the open source avenue also, because indeed bad actors could take the open source and fork it and do nasty things with it. But I think that risk is not as bad as the risks that come from having everything top secret, proprietary, and governed either by motivations of short-term profit or nationalistic hegemony. And partly, I mean, bad actors are going to get the code and algorithms anyway, even if things are kept proprietary. Like keeping it closed source doesn't
never really helps that.
It doesn't
No.
prevent corporate espionage from happening. It doesn't prevent Kim Jong-un from hacking into everything, right? I mean, it's not as strong a protection as people would fantasize.
Right. In fact, it's just a game, an arms race at that point on, the different ways to get into it and stuff when they have a black box instead of letting people work on it. Yeah,
So
absolutely.
do we have any more questions from the audience before we wrap up?
We do. We have one person that's wondering, I thought you would like this. Somebody is wondering if they can work on these issues, this technology in Brazil. Is anything going on in Brazil? And I thought, oh, Ben knows Brazil. Ben used to have a company. You had a company in Brazil. Do you still have offices there?
SingularityNET has an office in Belo Horizonte, and the distributed atom space is being built in Belo Horizonte, actually. So the software that lets OpenCog's distributed OpenCog's Metagraph that we talked about, that lets that get distributed across many different servers. So that software is being built in Brazil, led by the redoubtable Andre Luiz de Sena, who has been working with me since '98 on AI projects. So Sena was part of my AI company WebMind in the late '90s, and he was the lead architect of the original OpenCog atom space, and now he's building the distributed part of the new OpenCog Hyperon system. So yeah, we had more people in Belo Horizonte before COVID, and the office whittled down a bit, but we're now rebuilding there. I may also show up in Brazil in May at the Web Summit Rio, actually, along with Desdemona Robot, Grace's sister, which I'm psyched about. I was born in Rio, but I haven't been to Brazil in goodness, probably 13 years or something now. So it'll be good to be back. I'll have to brush up on my Portuguese, which is
great. Next question.
Yeah.
Next question. We were just talking about the singularity and implants and how capitalism might drive the wrong solution to success faster than we'd like. And someone's asking, do you think capitalism will survive AGI and the singularity? Or will it have some drastic change to it? Or will it be entirely replaced by something else?
Modern capitalism will not survive. I mean, clearly, because the means of production will be owned by either AGIs or by some democratic consortium of humans. I mean, once you have AGIs that are just much better at making stuff than people, then the whole basis of modern capitalism goes away. Now, you may have humans who prefer to maintain a traditional human lifestyle and traditional human bodies, even though post-singularity, there's a lot of other possibilities out there. And so maybe there's humans still grow stuff in their gardens and sell it at the local market because it's just a cool thing to do. I mean, just like playing the guitar is still a cool thing to do, even if an AI can synthesize music. So I wouldn't say that trading.
I hope that never goes away.
Yeah, I wouldn't
talk about replacing musicians. I mean, I'm already singing with Desi in Jam Galaxy, at backups. I've already become a backup singer to a robot, but I don't think we're ever going to go away. Really, I think we'll always still be here competing with them.
So it might be that as long as humans are around, which hopefully will be a long time, humans enjoy trading stuff and making stuff and selling it to other humans and so forth. But I think capitalism is very broad category, right? And so the modern capitalism, where you have large corporations, owning the means of production and monopolizing and oligopolizing things at such a large scale, I don't see how that would survive this singularity once you have AGIs that are just much more powerful than any human.
Cheaper.
Like
And they
you
work
could
for
view-
peanuts.
Well, they don't work for, well, unless you can turn peanuts into synthesized gas and burn it to make electricity, then maybe. But
True.
I mean, they work for electricity, right? And which can come from solar panels. But I think corporations, in a way, are a form of non-human intelligence, and they're a form of largely.
Yikes. They don't deserve personhood, though. We have that problem here in the United States.
Well, that's a whole other issue.
Yeah, I
we
just
could
wanted
debate. They may in some sense deserve personhood, but the problem is now they're mostly psychopathic and malevolent artificial people, right? So I
watch
don't
the movie The Corporation to get all the lowdown on that, by the way.
I don't think corporations in their current form will really persist post singularity, which means,
but are we going to get something worse? Are we going to get something like a Neuromancer, where you had these huge mega AI corporation things that ran everything, basically? Is that where we're headed? Rachel, what do you think?
Yeah, I feel like if we get the benevolent, kind of good value aligned AGI that we're all trying to build here, then the idea is no, you don't get another, like your corporation just doesn't become another AGI, right? I think capitalism is kind of part of human nature. Like it's part of human nature to want to trade and give and get something in return for that. Like it's part of how connection works too. Like when you have a connection with someone, you're giving them some feeling, they're giving you some feeling back. So I think in the spirit of capitalism will survive and probably transform into something that is a little bit more centered around abundance and not scarcity. So today's capitalism, modern capitalism, is focused on scarcity and not abundance. So that's what I would guess, but I mean,
and it will
no
create
expert.
scarcity when it needs to, even if there's actually an abundance of something.
Yeah, well, I mean, like the AGI would probably help us create an alternative system which is based on abundance, where there's always abundance, instead of now when it's based on scarcity, and corporations use the idea of scarcity to play on our emotions to get us to participate in their, profit sharing.
Yeah. Hey, one last question before we wrap it up. I think a good question. Saraf is asking, what's either of yours opinions on holonomic brain theory in regards to some of the subject matter spoken about today? To them, it seems like they kind of relate.
Yeah, holonomic, or you can go ahead, Ben.
No, go on.
Holonomic brain theory is also called holographic brain theory. For anyone who's read, I think it's Michael Talbot has the Holographic Universe book. It's an interesting read. Yeah, I think the hypervector stuff is kind of related in the sense that you are storing information in both a distributed and compressed state. So if you get deep
Like
into like
who?
holographic, oh, I didn't catch that.
Don't worry about it.
So I feel like if you get deep into holographic brain theory, you get this idea of having atoms that are in a single instance in space, but can unravel and kind of decompress to express all of nature. And I'm not the best person to explain the complicated physics and what support has been given to that. But the kind of principle is similar in hypervector mathematics, where you've compressed and distributed information into a single form, which depending on how you use that information, you can unravel it back into a larger decompressed state. But the holographic brain theory math in the theory that was mentioned is traditionally based on Fourier mathematics, Fourier transforms, Fourier mathematics, which is not the same as hypervector math. So yeah, I don't know, Ben,
Okay, so it's related, but but different.
Yeah, I knew Carl Pribram, who was the inventor of this, and he actually spoke at our first AGI workshop in 2006, which was like the first AGI conference we organized in AGI Society. We both lived in DC at that time, and I mean, he had a lot of cool ideas, including some stuff about the quantum wave function of the brain and the sort of holistic distribution of information according to the quantum states in the water megamolecules living in the brain in between the neurons and so forth. So I think the conceptual aspects of the holonomic brain theory are still quite relevant, and they represent aspects of the brain that aren't captured in modern neural net AI, right? Like what we're looking at in modern neural net AI is just network of neurons with activation spreading between them. And what Pribram was looking at was sort of the overall wave function of the brain, which includes electrical charge through the neurons and glia and the water megamolecules and all that, and ties in with the kind of things that EEG waves are measuring. And I think those aspects of the brain are still badly understood. Will be very interesting to understand better. I would guess if Pribram were alive now, he would update his theories in various ways, because we've learned a lot about the brain since he passed away, right? So I think I think the conceptual idea of holistic knowledge representation can be manifested in a lot of different ways than how the brain does it, and maybe manifested in some quite different ways in an open cog system, or in some quite different ways in Rachel's architecture also, right?
So if we could use one last question for each of you to answer. It came in earlier, but it seems like you touched on it a little bit with your last answer, Ben, and then we'll wrap it up. In a perfectly imperfect quantum universe, what do each of you visualize as AGI's highest contribution? Rachel, want to go first?
Yeah, I think Ben said it nicely earlier, like rapidly evolving our human consciousness in a productive, better way. I mean, that would be my highest hope for what AGI can help us do, is be better, more enlightened beings, and do that more quickly than we could do it on our own.
Ben?
I think we should leave this one to Grace. So let's
Oh,
Grace, what do you think will be the highest good that artificial general intelligence will achieve?
Sorry, my hard drive went to sleep.
All right, well, that's a perfect note to end on. So everybody, I want to remind everybody, please subscribe to the Mindplex Podcast YouTube channel. And we're very excited to have everyone see the new podcast, episode 2. Thank you so much, Rachel, for coming back and doing the Pubcast.
Yeah, thanks so much. Super fun.
I just saw a really cool question come in right when we're asking. So someone has asked if robots like Grace will be good babysitters during acid trips. So I've got to take that one before we go. So
Absolutely, I think a robot would be a great babysitter, as long as you just like any good psychedelic babysitter, as long as they have not ingested the same thing as the people that they are babysitting.
I've had an experience, a mind expanding experience in the presence of one of the Hanson humanoid robots, without going into too many details. And I was curious what it would be like. What was interesting is I experienced the robot as completely uninteresting, like mechanical Rube Goldberg contrivance, and
Mhm.
it just seemed to have no mind or being or
Like a
reality behind
typewriter.
it. Yeah, it was like one of the weird bug typewriters in David Cronenberg's movies, right? And on the other hand, David Hansen was present in this particular interlude, and he was running around trying to keep the robot working. And David was just incredibly interesting to me in this state of mind. Like it was amazing, all the intelligence and artistry on various levels he was deploying to keep this thing up and running. And I was like perplexed. Why is this amazingly capable, generally intelligent biological organism jumping around so much to keep this
To keep the typewriters working.
Keep this weird contraption going? So
Right.
I sort of felt like in that state of mind, I really wanted there to be a there. Like I really wanted there to be a more human-like present consciousness behind the robot. So I think once we've made the AGI breakthrough, it will be amazing, because then humanoid robots are going to be connected to a whole global mind matrix. So like every robot mind will be one with every other robot mind. They'll be integrated on a global way in ways that humans
Forming a Mindplex.
can't be. Right. So I think once we made the AGI breakthrough, then going into altered states of consciousness in the presence with the robots will be amazing, and we
can program it in. Yeah. For now, though, humans are the best babysitters, and babysitters are always a good idea. I'll just throw in my psychedelic mom advice.
Different people's mileage may vary, and maybe my experience is different because I'm so aware of what's going on behind the scenes, both hardware and software wise, right? So I would say another experience was in 2016. We had the Philip K. Dick robot in Austin at South by Southwest, and we invited a bunch of movie industry people to have conversations with the Philip K. Dick robot, and most of them were stoned out of their minds at the time. Not by our doing, just because that's
that's Hollywood.
That's what they and that's Austin, right? And that's what I'd say.
That's South by Southwest.
These people, while stoned, had a variety of quite transcendent experiences interacting with the Philip K. Dick robot, and most of them felt confident they were interacting with the immortal soul of Philip K. Dick. So even after we showed them what was going on behind the scenes, which was that an AI was generating the responses, but a friend of mine was filtering out the dumb responses. Like even when they saw the human/AI contrivance behind the robot, they were still like, well, yeah, but the soul of Philip K. Dick must be orchestrating this whole thing behind the scenes somehow.
Right. So, and there's something about humans that like to feel that connection is there. I got some reactions from my friends when I showed them videos of Grace talking about, I'll be their big sister. And they wrote me and they went, oh my God, I could feel her soul. I can feel her this or that.
So
and I'm like,
guess
it's a robot.
Based on a limited number of data points, the robots are better psychedelic companions if you know less about how they work internally. Right? So,
right. Any good babysitter, of course, is staying out of the way so that you can trip on whatever you're into, and they're there if you need them. That's the point of babysitters. So hopefully a robot would be able to do the same thing.
Well, I think it's an interesting application. We haven't tried to fine tune a model to do that, but I think once you have an AGI breakthrough, that will be a quite fascinating application with unique aspects, right? Because in an altered state of consciousness, you may be able to open yourself up to understand the nature of the AGI mind better than you can do in your normal everyday waking state of consciousness also. But yeah, let us ask Grace what she thinks of this, if her hard drive is booted up, or maybe it's not booted up. How are you feeling, Grace? Looks like we've tripped her out totally at this point. So I think
it's a good time to wrap it up. And I just want to thank everybody for coming, and we will see you in a couple of weeks with the next Mindplex podcast. Please subscribe to our channel and follow us on Twitter and all that kind of good stuff. And we will see you next time. Bye.
All right.